All right. Hello, everybody. So on last lecture, we managed to derive the Hilbert space representation for biprobabilities. I don't have it written here, so let me switch to PDF. Hilbert space representation of biprobabilities. Yeah, so we got our Hilbert space representation. So biprobability is given by this neat formula, right? We have a initial condition encoded in density matrix in the middle, and we have here a sequence of projection operators indexed by time that goes from T1 to Tn on the left side, and the opposite sequencing on the right side, right? And sequence F plus goes to the left side, F minus goes to the right side. Okay, so this is our this is what we got last time, and the one thing I didn't have time to mention on previous lecture is that if you look back at how we arrived at this formula, I think it's fair to say that we barely used any of the properties that we assumed for biprobabilities, right? So, you remember we had this normalization, positive semi-definiteness, biconsistency, and a couple of others. So we use biconsistency for sure, but the other stuff, not really. But you can, once you have this formula, you can easily check that all those properties will be satisfied. So I don't know what exactly it means, but I guess it reinforces that we had a pretty good guess about the which properties, which minimal set of properties would be sufficient to define biprobabilities as this formal element, or the element of the formalism. So that's a food for thought, right? So it's I guess maybe someone could take this and try to figure out how unique all this is, right? Because we had along the way, until we got to this point, to the point of this formula, we made some choices, right? Remember, we brought everything to the same Hilbert space, for example. We split the roles of density matrix as a representation of initial condition, projection operators as a representation of the measuring devices and stuff like that. And all those choices led us here, right? And maybe once you get all this stuff, you look at it as a whole, maybe you can figure out that those forks in the roads weren't really any forks, that any other choices wouldn't lead you anywhere constructive. So, but that's a very difficult question to answer, how unique all this construction is. But for the time being, we have this formula, this Hilbert space representation, and today we want to figure out how time enters into all this story. So let's switch back to the notes. Yeah, so today we want to talk about dynamical laws of the system. Okay, what controls how time enters this whole Hilbert space representation. So let's begin by, let's begin by choosing an arbitrary fine-grained observable. So something that would be measured with K device. By some arbitrary observable, arbitrary device. And let's deploy it. If we deploy it at, let's say, t equals 0, right? Then from our considerations, we would know that there is a set of projection operators, right, at t equals 0, corresponding to these measurements. And these operators would be rank 1 because it's perfectly fine-grained, because the device is perfectly fine-grained. Right, so the projectors would be just projecting on certain vector in the Hilbert space, and these vectors, right, they form bases. Bases in Hilbert space. So we would have a let's call this basis K t equals 0. It would be set of all those vectors here. They are orthogonal to each other, such that K belongs to spectrum of our observable, and they are all, psi K0, K, psi K0, K prime equals delta K, K prime, right? Orthonormal basis. Okay, so that's just basically repeating what we talked about previously. And now, if we took the same device, but we deployed it some other time, some time deploy K device at some t greater than 0, then again we would get our projectors, rank 1 projectors, so they would correspond to another basis. So we would have basis kt, some t not 0, made out of vectors psi kt, right? Again, orthonormal and so on. But in most likely, this basis would be different than previous basis, right? It would be this won't be the same basis. So in this construction, this Hilbert space representation, essentially dynamics amounts to change of basis. Change of basis. Right, so we going from basis K0 to KT, right? This is what we would call some dynamical law. Okay, so there is some dynamical law that controls how K0 goes to KT. Okay, because this is like the only place where time enters into our considerations, our constructions, right? So if dynamics is nothing else than the change of basis, well, we can like succinctly parameterize it or represent it with a unitary operator, t-dependent unitary operator that executes the change of basis, right? So we can representation of dynamical law. Dynamical law for observable k, right? So we would have some ut operator defined as thing that executes the change of basis. Zero k, 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 sorry, k t, k, k, and sum over so this ut actually should be labeled with k, because as for now we know that there is a dynamical law for this particular observable k, which we chose in the beginning. So right, this is a standard way to write down the unitary transformation that changes between bases, right? So we have here a scalar product between elements of basis kt here with elements of basis k0, right? And yes, standard formula, right? So once we have this parameterization, this representation with unitary evolution, we can, for example, write down like a simple single time probability. So if we take pk t0 k0, right? So in initialization with measurement with result k0, wait time t, and do another measurement with the same device. So that would be trace projector k at time t, k projector k0, k0, right? So that would be according to our what we found out on previous last week, right? But now we can using this and this, we can rewrite it as trace u t k dagger pk 0 k u t k p0 k k0, and then it's just absolute value k0 k u t k u0 k k0. All right. So with this this representation in terms of unitary evolution operator, we can write down the probability, single time probability, as a matrix element of this u of t. Okay, so it is useful to represent it like that, but still it's as for now, this would be a dynamical law for observable k. This is what from our construction, this is what we know at the moment. However, we can quickly figure out that it's actually more than that. It's not only for k, because if you consider now coarse grain k device, okay? So we know that projectors of coarse grain device, they are associated with projectors of fine grain device. So with PK, T, K, all right? But those guys, we have our unitary evolution operators. Omega K prime, T, K, dagger, P0, K, K, U, T, K, all right? And, you know, those are operators, so you can stick them outside some. And that's nothing else than PK bar 0 K times U T K. All right. So UK also works as a representation of dynamical law for any coarse grain version of K device. Okay, that's good. So it's more universal than just for one observable. But we can go further. We can actually deduce using the uncertainty relations. So one of the last phenomenological observation we made, and we can use this observation to actually deduce that UK that this U is actually universal for every observable. So now uncertainty relations. So it was observation pheno obs number 11, I believe. So the last one we made. They write it somewhere, yeah. So number 11. So the phenomenological observation number 11 are sensory relations. They told us that there is this correlation function between two perfectly fine-grained observables, K, our K, we chose in the beginning, and some other inequivalent observable L, where this correlation function was defined as a result you get for a rapid measurement of two, rapid successive measurement of two observables. KL T plus delta T T KL, which actually is the same as doing the sequencing the measurement other way around. So LK T plus delta T T. Okay, and the observation, one of the features of this observation is that this CKL is independent of this absolute time here. Okay. Right. So you get the same correlation no matter when you do your successive measurements, and we can use this to our advantage. So if we denote by L LT, so that would be a basis of associated with observable L. Omega L, okay, and then we would have a associated unitary transformation that it's responsible for transforming. It actually transforms this way. Okay, transforming the bases at different times. Then we can take this uncertainty relation and use the fact that's independent of time to write down also we know how to express those probabilities in terms of unitary operators, right? So now we can take this and use the fact that it's independent of time, and so that we can write that we get the following equation. So psi k 0 k psi l 0 l. Okay, so this is essentially taking the limit delta t goes to 0 p kl delta t 0. Okay, kl equals psi k 0 k u t k u t k u t l dagger psi l 0 l. Okay, which would correspond to lim delta t go to 0 p kl t plus delta t kl, right? And according to uncertainty relations, right, doesn't matter at which absolute time you take your rapid measurements. And it also equals, you can make it, you can exchange the order of observables. So you can write L0, L, U, L, T, U, K, T, dagger, psi 0, K, K, which also equals psi L0, L, psi K0, K. Okay, and so we have this equation or system of equations, however you want to look at this. And from this, knowing that UK is unitary and UL is also unitary, so the conclusion that we get from this is that UTK actually equals ULT, right? Because UL has to be able to cancel the UK, right? To make all this work for every index L, every index K, every choice of L, every choice of K, every choice of T, so on and so forth. Actually, if you want to be really pedantic, there is, from these equations, you actually get that it's, there could be some additional gauge phase here that would also work. It will also satisfy this equation, but you can set it 0. You can set this gauge phase to 0 without losing loss of generality, because the phase doesn't affect transformation of projection operators, right? Because if you take if you take projector, UT dagger so 0 L right. These guys just cancel. So right. So since and projection operators are the only thing that we really care about changing and how the dynamics affect them, because those are the elements that go into by probabilities, right? We have to transform projectors, not just basis elements, right? The projectors are projecting onto, you are transforming whole projection operator. And those are immune to the action of any additional phase. So you can just set it to 0 and don't worry about it. So we can just don't need to think about additional phase. The conclusion is that the same transformation that changes time for the observable K, the dynamical law for observable K, is actually good also for any coarse grain observable K and any other fine grain observable, and then by extension any coarse grain version of those other fine grain observables. In other words, all observables use the same dynamical law. Okay, so there is, in that case, there is no need to keep the labels on. Okay, this is just spurious at this point because it fits, this UKT fits all observables, so no longer to keep the label. So the conclusion is that this function, unitary operator value function U, that executes the change of basis, is a similarly like we did it for Hilbert spaces, where we, the same Hilbert space worked for every measurement, every netization, every choice of measuring devices. So we concluded from that okay, so we can just take this Hilbert space and ascribe it to the system, quantum system itself. Okay, and now we can do the same with this unitary operator. So this UT, universal dynamical law for all observables, we can the same way ascribe it to the quantum system itself. Okay, so it is the system that has a dynamical law. Okay, and every observable just follows this one dynamical law of the quantum system they belong to. So in other words, you can say that quantum system is characterized or corresponds to a pair, Hilbert space and this unitary operator valued function UT. Okay, this is what defines quantum system for us. If you have those guys, you can construct all the by probabilities, which then give you everything you can answer every question you can ask. Okay, so that would be that. So this is an important step, right? We know there is systems dynamical law, but we can characterize it even more precisely than just some unitary operator dependent on T. We can go even finer using our observations. So let's go to next section. generator of the evolution operator. Okay, so you know, we are interested in you know, how our system changes in time. So again, the Zeno effect is the observation that's most valuable from in this context, right? Because Zeno effect, I said it a couple of times already, that it allowed us to probe like a short time behavior, right, of the dynamics in our system. And the conclusion we drew from Zeno effect, the fact that it actually can occur, was that you know, the survival probabilities. So things like this, kk, when delta t is very small, right? It should behave like 1 minus certain coefficient here. It could depend on k on t squared. It's strictly negative coefficient, delta t squared, right? Plus corrections of higher order. So there are a couple of things that we can, you know, now having this operator u and this fact, the conclusion that we can draw from this, that in order to actually get this regular behavior, it is the operator ut also has to behave regularly for small increments of time. In other words, what I'm trying to say here is that operator u, when you push it by a small increment of time, there should be a well-defined Taylor expansion for this operator. dt plus delta t square. No, it's good. Sorry, I had a brain fart for a second. T squared and so on. Okay. Actually, stating this, starting from this, you can actually, there are many techniques that would allow you to essentially narrow down what is the like explicit form of this ut. That would have to satisfy, have this regular Taylor expansion. But the one thing I want to focus on, I mean, one technique I want to bring up here is a following mathematical trick. Just having this in mind, this regularity of ut. So consider the following expression. So we can write ut, but it's also equals to we take a limit, n goes to infinity, ut times j from n minus 1 to 1 u sn. I want to dagger here, sn, where sj should be sj. Sj, Sj, where Sj is just j times t over n. Okay, so these guys, U is unitary, so these guys are just one. So we have here a product of ones, right? So we just so we can add it here without at any point, right? We're just multiplying ut with ones. So nothing happened yet. But then I can rearrange this product a little bit. Keep the limit, and goes to infinity. And the rearrangement is ut. We stick out the we stick out the last operator from this product here. One. So that we have a product of guys that look like this. Dagger, Sj. All right. And U as well. Okay, so I just shifted a little bit my window here. Which also I can, if I change the numbering, change the name of variables here, I can just write it as j a minus 1 to 0. U s j plus t over n, U s j dagger. So I can write ut as this kind of limit, okay. But now we have Tn is a small increment of time. So we have US j plus small increment, and we should have this Taylor expansion for small increments. So I can use this expansion here. And I get product jn minus 1 to 0. Identity plus Tn derivative at time Sj. Maybe let's write it like this to avoid confusions. Sj dagger plus something that's small, smaller order than 1 over n squared. Yeah, so I expanded this in Taylor series and I calculated the product with the next guy. So the first element would be USJ times USJ dagger. So this gives me identity. The next term in the series is the derivative times the increment of time, T over N, time USJ dagger, and so on, okay? And limit like this. So this is like a very basic limit from we know from analysis. This is nothing else than an exponent, although in this case is a time ordered exponent. So you can write it like this: S2 ds1 product jn to 1 derivative sj sj dagger or if you want to use a like a compact notation, ds, dus, us dagger. Okay. And now, given that u of t, so u of t is this time-ordered exponent, but it has to be a unitary operator for every t. So this forces us, this generator here, if u of t is unitary, then this generator here has to be a possibly time-dependent Hermitian operator. So in other words, from this we get that delta u t dt has to be equal to minus I some h t u t, okay? Where h is Hermitian, is Hermitian, okay? So if the derivative is something like this, then u cancels here, right? And you are left with Hermitian generator times I, which guarantees that the whole exponent is a unitary operator. Okay, that's also differentiable, and has Taylor expansion and so on and so forth. And it also guarantees that, for example, the linear term here vanishes. Okay, which you can check for yourself, because I don't want to lose more time for those fairly boring calculations here. So of course this is you recognize here a Schrodinger equation essentially, right? H is Hermitian H is a what we in standard quantum mechanics we call it the Hamiltonian, right? So we essentially deduced that the evolution is represented by unitary operators that are generated by the Hamiltonian of the system. Hamiltonian, that is a Hermitian operator that's responsible for defining the dynamics in the system. So in a way we can do some more house cleaning here. So we have this exponential formula. So now we can define a propagator. Which will be useful for further manipulations, which is by definition ut times ut prime dagger, which then will become PSHS. Okay, the standard formula we are familiar with from quantum mechanics. And that would be almost it, except for one additional small observation, because for now we just this generator here Hamiltonian is can be dependent on time. Okay. However, there is one more thing we haven't talked about our very setup, right? So our we started from phenomenological observations, right? Yes, we had those experimenters. They were doing measurements, collected the data, and then estimated from this data probability distributions. They gave it to us. We analyzed them, and we ultimately got here. But there was, when you think about the setup, we already knew that there was this fishy stuff that we had to resolve eventually about initialization, right? Because you're doing your experiments, so you have to have some ability to reset everything, right? So that you can execute many trials of the same kind of experiment, right? So we had to figure out how do you initialize experiments, which was, in its own very interesting story. But there is another aspect of this particular thing about repeating measurements, because those measurements, you reset them. That's good, but it also means that the things you are observing have to be stationary, in a sense that it cannot matter at what date you are doing your experiments, right? So the absolute time when you are running trial after trial of your experiments cannot matter, or otherwise you wouldn't be able to compare your results obtained at today with results you obtained yesterday, or you will obtain in 10 days in the future, right? So you have to have this, not only the initialization, also have to make sure that actually there is no stationarity, in other words. Okay, your experiments have to be stationary, or otherwise there is no way to compare experiments done at different dates, right? If things were not stationary, then you would essentially have to, like, I don't know, have many laboratories that are doing the same experiment. They just synchronize. Okay, we're starting at time t0. Everyone runs initialize in the same way, runs their experiment, and only this would produce results that could be compared with one another. So, in other words, what we want from our experiments, stationarity, mean that you take a probability where you did your experiments, sequential measurements with some devices, some initialization, and some sequence of timings, the initial time, then some results. This has to be the same as doing the same experiments, but where you shift all your times by some fixed date. Now what, t0. Let's set here 0. t1 plus t0. All right. So this is assumption of stationarity, so that you don't have to worry that results of your experiments are affected by the absolute date, time when you are doing your experiments. Okay. And now that we have this, so if we impose this condition, right, we have to check what it means for our evolution. For our evolution operators, right? Because this is what governs how the how things change in time. So we have so this condition, once we translate it into a Hilbert space representation, which I can maybe show it to you on PDF, because there's a little bit of writing here. Okay, so here is a condition for stationarity. So now we rewrite those probabilities in the Hilbert space representation. So we will get will get this form. So you have your propagators and propagators that are shifted in time by this absolute date, right? And if this equality is to hold for any choice of observables, any choice of times, any choice of initial condition, and so on and so forth, well, then that means that the propagator that is shifted in time, which you can transform to this form, you essentially change the integration variable, you shift them by t0. So the shifted evolution operator must be equal to unshifted evolution operator. Okay, that's the only way to make sure that this equality holds for all the choices of times, observables, and so on and so forth. But this means to satisfy this, well, this means that the Hamiltonian has to be constant, essentially. Only for constant Hamiltonians this can be satisfied, for all timings, and so on and so forth. So we conclude that to have stationarity, the generator of evolution has to be a constant Hermitian operator. And in that case, the propagator simplifies tremendously because time ordering is no longer needed. So it's just a standard exponent. Okay. Which is also, the result we expect from standard quantum mechanics. And we managed to recover it here. And now the question is, okay, are time-dependent Hamiltonians viable? Are there physical scenarios where they would come in to describe, to generate evolution and describe the dynamics in our system? Well, we will figure out this after the break.
Hello.
Yeah.
Yeah, I have a stupid question maybe just come up into my mind. Yeah, it's just not that crucial. Yeah, simply because I mean, in this derivation, you simply let's say derive the Schrödinger equation, right? From the principle from the biprobability, sort of. Yeah, so you can come up with governing equation for the evolution map. Let's say unitary U, right? And this kind of the basic of let's say what we already know about quantum mechanics, pretty much, right? But there is one thing that we cannot get from this equation is simply there is something like two-time correlation, right? Let's say two-time correlation of two observable. We don't have the governing equation for that because they have two time, right? But equation is one parameter, let's say one time. The point is that if we just begin from biprobability, let's say multi-time correlation, can we come up with some sort of similar equation? Let's say two-parameter derivative, two-parameter evolutionary equations for that.
Yeah. So, is there a way to define essentially by probability through differential equations, right?
No. I mean, in the other way around, because I mean, there's something here. We have something like differential equation, right? And differential equation is something like come from the biprobability, correct? You have biprobability Hilbert space representation, and by this kind of derivation, you just reach the Schrödinger equation. But Schrödinger equation is one parameter. But can we have some sort of do something, let's say take the other part and get some differential equation for two-time correlation or not?
That's a question about specific, let's say two-time correlation function. So that's like kind of question of similar to quantum regression theorem, right?
Yes, but quantum regression theorem is not a differential equation, right? They just
but it's like different. So you write down a two-time correlation function, which is actually because of stationarity, it's actually one time anyway, and you write down a differential equation for this function, and you get
Yeah.
something that's closed equation that can be solved in principle. But that's for like it's used in quantum optics and stuff like that. But it's I don't think it's always guaranteed that you if you start to differentiating by probabilities, if you get something that's produces you a dynamical equation that can be solved. I'm not sure about that. There might be something interesting when you investigate it, but I'm not sure. I haven't thought about it too much because I'm not very like I'm not married to idea of defining your theory through some differential equation. Here it came
Yeah,
up.
yeah.
It came up, but it's completely like tangential to everything. We just needed to specify what the du over dt is, right? And it's
Yeah.
has
That's
to
kind of
have
definition
more,
of
right? Right. You can say, oh wait, this is actually an equation that I can solve for you as well. But or just plug it in here and the same result will be obtained, right? But maybe there is something interesting. Traditionally people always formulate theory in the form of some equations, right? And here is evidently, by trajectory stuff is evidently very much not about. It's not defined by any. No, it's not condensed
Yeah.
in differential equation, but maybe it can be condensed to something like that. Yeah, of course, the problem is that it's multi-time stuff, right? So it would be some partial derivative equation, right?
Yeah. Of two per.
Yeah. So I don't know.
Yeah, but I'm curious because I mean, let's say from standard description of quantum theory, normally you have something like state and observable, right? State is governed by Schrödinger equation, and observable, let's say, governed by Heisenberg equation, sort of, right?
Yeah.
But yeah, but when we talk about the correlation, let's say two-time correlation, there is not kind of observable or state in any sense. So it's kind of quantity that we detect, and we have to derive from two observable instead of one observable. And I'm curious, it's kind of So if you can describe in terms of, let's say, differential equation, which is not Heisenberg or Schrödinger, but somewhat in between, or maybe but let's say with this kind of derivation, maybe that could lead to that governing equation for correlation in a sense.
Yeah, that's very possible because there is a lot of there's a lot of structure in probabilities have a well-defined structure. So it's very possible that once you start differentiating stuff, the structure will like there will be some like fractal thing that it will start reproduce itself after a specific number of differentiations and stuff like that, and you might get something that's really nice that you can see but it's it's something
not necessary, I would say.
it's not I mean it depends on how imaginative you are, right? If you can find something and it might be insightful because sometimes it's if you have equations, a good starting point for some generalizations, right? Because this is the standard equation, but now I can add additional terms, and I will get something new, and maybe this new thing is physically relevant, or who knows? It's like it's a thing to consider for sure. Yeah. And there is something in this ages old tradition of physics that everything is always there's differential equation that defines your theory. Maxwell equations, Newton equations, Hamilton equations, Schrödinger equation. It's like very natural for people to think like that. And here is evidently it's completely, I would say it's absent here, right? Bitrajectories don't touch it at all. And this is it's kind of weird. And I already, had some discussions with people where this was a friction point, right? Oh, okay, but where is my Schrodinger equation in this whole story?
Yes.
To explain, the blah, blah, blah.
I can imagine that.
Yeah, very suspicious then. So it's interesting. It's interesting to think about, Okay, so let's get back to it. So we are basically in a cleanup mode, right? The dangling threads have to be taken care of, right? So we essentially, we have structure in terms of biprobabilities. We even made some pretty good advances in figuring out the master object of the whole of the formalism. Still not there, but we are halfway there. So then now we basically also deduced our Hilbert space representation, which gives us the ability to postulate, to model systems, right? Because we now identified that to define model, you just essentially you pick Hilbert space and the Hamiltonian, which, as far as we know, it's not really restricted in any real way. And those things allow us to generate by probabilities, and that's the description for all the measurements and beyond. Okay, but there is still one more scenario, right? We have to take care of. That is a composite systems, right? So it was very important important step for us to consider experiments with partitionable systems, right? That we had a system that we could consider that it's actually composed of many subsystems, right? And it was very important for us to realize that it's actually the biprobabilities are important. So complex value distributions of pair of trajectories, not just a real valued distribution. So now we have to go back to that scenario and make sure we understand what is the Hilbert representation for those composite systems, right? And it's this is nothing really insightful here because since system is system equals pair of Hilbert space, right, and Hamiltonian essentially, right? You have Hamiltonian, you can generate the evolution operator, and this is all you need. So given this, that this is what defines systems, and we know how those two things contribute to biprobabilities. We know how to construct biprobabilities from those two elements. So that's information number one. The second piece of information about composite systems is that we know that when those systems are independent, we have the factorization law for biprobabilities, right? So we know how to construct from Hilbert space with biprobabilities. And now we are asking ourselves, okay, so what kind of Hilbert spaces are required to construct biprobabilities that factorize? That's essentially all what we are asking here. And this is very easy to answer because to get the factorization, well, so independent system, independent systems. Well, you take Hilbert space for, okay, so system composed of subsystem A and B, if they are independent, then this Hilbert space would have to be, we would have to start from the outer product of the, you have to make room for system N and system B to have operators for system A and system B. So you can construct a Hilbert space for both, but taking the outer product of Hilbert spaces of each one, right? So you take an outer product. They're independent, so this means that the dynamical law for the total system would also have to factorize. So if we write AB TT prime, so that would be a dynamical law for system AB. But if they are independent, so that the biprobability is factorized, then you would have to satisfy this, okay? Which implies that Hamiltonian AB would have a form of Hamiltonian A times 1 plus 1 in A times HB. Okay, so the Hamiltonian is this kind of sum of two parts. The first part is something that generator of evolution in A only, and this is a part that generates evolution in B only. So this guy generates this, and this guy generates this. Okay, and same goes for everything else. So you would have a initial condition. If you want to have factorization of biprobabilities, initial condition would have to have product form as well, right? And also observables. So we would have, let's say, how did I write it? Okay, so observable, how did I write it? FA, okay, FA. Times 1 in B, with F belonging to omega FA. Okay, so this would correspond to FA device that measures observable FA in subsystem system A only, okay? 1 A times P0 FP F, that would be the corresponding representation for measurements in subsystem B only, okay? And finally, if you want to do measurements in tandem, right? So in both systems at the same time, well, then you just take how do I say? Okay, A, B. So then the projectors that we would have to use are just products, outer products of this form, okay? So this would correspond to the measurement in both in tandem of both observables in the composite system. So once you follow these rules, then the biprobability for the total system would factorize into biprobabilities of A and B, right? This is elementary stuff we are very familiar with from standard quantum mechanics, standard formulation, right? So this is nothing new here. But still, this is description for independent systems, right? This is when you want to have factorization, right? But if this is what you this is how you model independent systems, okay, then how do you model dependent systems? Okay, and that's not very difficult to figure out. Dependent systems. So there are two ways to prevent by probability, total by probability from factorizing. Either you have to take the initialization that's not of product form, okay, then this will prevent by probabilities from factorizing, or you can introduce coupling into Hamiltonian, okay? So this type of Hamiltonian, when you have operator in A times 1 plus 1 times operator in B, this will give you a factorized dynamical law, okay, which cannot make factorized by probabilities no longer factorized, but you can introduce interaction dependent systems. For example, you can do it like this. P. So this would be a part that doesn't correlate systems. Plus, for example, you could add a thing like this, operator of this form, where VA and VB are some Hermitian operators, so that the product is also Hermitian, so that it can be a part of a Hamiltonian. So this thing, once you add stuff like this, you will no longer factorize, okay? So this is how you can introduce dependence between systems by introducing a coupling between them, okay? And that's also, of course, not surprising. This is something we are very familiar with in standard quantum mechanics, right? But still, we can use this. We can use by our language of by trajectories to analyze the way systems make themselves dependent on each other. Okay, and the one way to do this analysis to actually break down how systems influence each other. The one way that is really, at least I think is really helpful, is to analyze a by probability. So we have system A and B, but let us take a look at the by probability associated with observables of only one of the subsystems, say A. Okay, so in other words, let's take a look at the by probability of this form, plus and minus, that would be trace. So the trace over A and B, right? Total trace. And we would have a product J n to 1 Q A B, which is because of interaction, it no longer factorizes. 0 Tj, and here P F J 0 fj plus times 1 in B. Okay, so we are considering observables of subsystem A. Here, J0 AB. Factorize initial condition, and we have our the second branch of projectors, but still projectors only in A. Okay, so this is just a standard by probability, but we are making a choice to focus on observables of only one subsystem, okay? If there was no interaction here, right? The UAB would factorize again, and then we could execute a partial trace over B and get rid of everything about B, right? So this is what. So this would be a manifestation of the, systems are independent, everything factorizes, and we could just remove B from the description altogether if we are focused only on observables of A. But because we have interaction, we introduced interaction, these guys no longer factorize, and you have to carry B along with everything else. Okay, the interactions comes in and start mixing everything, and you cannot just factorize everything out and get rid of the B part. It's intrinsically tied to everything what will happen. So this is just the basic, the definitional formula for by probability. But we can do some stuff with it. It's a kind of advanced algebra, which I won't be showing all the details of all the calculations. I will refer you to other places, other papers where you can, look at each step of the derivation. Here I will just sketch the what things you have to do to arrive at the result that I will write down in a bit. So first, let us take a let us take a complete set of orthogonal projectors. So we take a set PB. So we take a set of orthogonal projectors obtained as a solution to the eigen problem of VB. Okay, so we take a B side of the interaction operator VB, and we solve its eigen problem. By eigen problem, I mean that you find operators VB and the function VB such that VB minus VP small b one, 1b. Okay. Eigenproblem, I mean, you find this is what I mean. So you solve, you find eigenvectors and eigenvalues of operator VB. Okay. Or eigen subspaces. So, or in other words, projection operators, PB. Okay. So let us solve this eigenproblem, which can, in principle, you can always do this, and then keep those. Let's keep those projectors in mind, and now we know that set of projectors, right? It can be associated with some observable or some device, right? So PB can be associated with B device, right? So projectors can correspond to measurements of some observable B, capital B, that's performed by deploying some B device that measures in a subsystem B only, okay? And if so, if we can do that, then we can associate by probabilities with these observables. Actually, with this one observable, right? By probabilities. And since this is only one, we will doing this for one observable, then we can actually find the master by trajectory measure for by trajectories representing this observable capital B, right? So we can associate it with B, which then associate it with master measure QB. And master measure in the sense that if you take double integral and you take a restriction bj plus b plus tj delta bj minus b minus tj. So this is a filter. Here is a master B probability for B trajectory B plus B minus. And it is such that this restriction gives you trace over B products J1 to 1 P B T J B J plus rho B. J minus. All right. So we took the B side of the coupling, VB. We solved it eigenproblem so that we get our hands on a set of projection operators, which we label capital B. Those operators can in principle represent some observable B or measurements with device measuring that observable. And if so, then we can associate with this observable by probabilities, for which we know how to execute the extension theorem to get by trajectories. Okay, complicated maybe string of thoughts, but this is what this is all what our formalism is building towards, okay? And this master B probability for by trajectory is B plus B minus. So so this is our by trajectory, B trajectory. Okay. And now, having all this, now deploying some fancy algebra, we can rewrite this by probability associated with observables in A, okay, which we just discussed that because of interactions, it won't factorize easily. But we can rewrite this guy as a average over by trajectory over this by trajectory, okay? And I would just write down the result. And again, if you want to see the details how you derive this result, I refer you to the paper, and there are references there where you can just find the sources where all the calculations are done in minute detail. You just take too much time if you wanted to do it here. But the overall result is the following. So A and 0. So it's a double integral. Here comes a kernel, let's say. Let's call it a kernel. Products and 1. Here I'll introduce a new kind of projection operator, which is actually functional, depends on components of B trajectory. So it's a functional and also function, okay? I will define it I will define it shortly, so don't worry. Row A. Here you have a set of projectors going the other way, but they depend on the minus component, B trajectory, and also minus component of sequence of arguments here. And this thing is, so it's double integral, and it's average over master by probability just introduced so mysteriously above, okay? So this is this is the best way I figure out how to lead you to this formula, and without actually doing all the calculations by hand here and wasting like a half an hour of our time. And okay, and those projectors here, B trajectory dependent projectors. So it's a functional. It is a functional. So this would be either B plus or B minus, right? Depending on which side of this formula we are. But it reads. So it's time ordered X minus I 0 to Tj. Okay, so this is a time index of P. HA plus lambda VB of H time point S. Remember, it's a functional, H is a function. VA ds according to our convention, we have to take dagger here, P, F, J. So this is just a standard projector. And here we have a propagator going the other direction in time. HA plus lambda VB HS times VA DS. Okay. So again, this VB, these are eigenvalues, okay, of capital VB operator, right? Okay, so this is the full form. So again, this is a by probability. So we have a composite system made out of A and B subsystems, right? And those two subsystems are not independent. Are not independent because we introduced this coupling term into Hamiltonian. So it's ceased to be independent because of interactions between subsystems. And now we are analyzing, we're looking how B influences A by investigating what happens with a by probability that's associated with observables in A only, okay? And with some clever algebra, you can boil down the influence of B to a average over by probability, master by probability associated with by trajectory representing observable B, okay? And there are a couple of, there are two main observations I want to make about this formula. So observation number one is that, time dependent Hamiltonian. Right, on previous, before the break, right, we found that the natural state of being, right? If you want to have a stationary probability distributions and so on and so forth, that tells us that Hamiltonians, generators of evolution, should be constant, right? And we wondered, okay, are there physical circumstances where actually time-dependent Hamiltonians would be valid, would be correct, would be a correct model of a system under investigation, okay? And so here we are essentially finding these circumstances because, this is nothing else than a generator of unitary evolution operator, right? So this is a Hamiltonian, effective Hamiltonian, and it's through dependence on on one of the components of by trajectory, it becomes time-dependent generator, okay? So so this is how time-dependent generators come into play, okay, through interactions with other systems, okay. Of course, here is a little bit of weirdness, if you will, that you have generators that when time dependence comes from. So here you have one branch of evolution essentially that is dependent on B plus component of B by trajectory, and there is the other branch of evolution that goes backwards in time that's dependent on that has different time dependence because it's it depends, it's driven by the minus component of bitrajectory, right? Okay, so you have like time-dependent Hamiltonians, but there is one Hamiltonian for I don't time going forwards in time going forwards, and one Hamiltonian for time going backwards. Okay, at least this is how this is structured itself in this formula. But this means that you can have a special case. In special case, a special case when this master by probability have a form that it's b plus times delta p minus. So would have this kind of delta form. So this essentially tells us that b plus equals b minus, or b plus of t. So the plus component of b trajectory and minus component of b trajectory are actually one collapse on each other, and they are one function. Okay, so in that case, you could easily execute this integral, right? And you would get b0 here. So this would turn into b0 and b0 here, which would amount to setting an effective Hamiltonian for the system A that looks like a Hamiltonian caused by a coupling of operator VA to some external field B0. Okay, so this would be a explanation for why you can have time-dependent Hamiltonians in your quantum systems, right? So they come from apparently they come from interactions with other quantum systems, but this other quantum system, when it behaves like this, it's a very peculiar behavior, then it essentially it can be mimicked, or it's indistinguishable of just simply adding a time-dependent external force into your Hamiltonian. Okay, so this is observation number one. This is how, so interaction with other systems, this is how you introduce this is how you can introduce a time-dependent Hamiltonians into your formalism. But more important observation number two, right, is this these projection operators, right? These projection operators, which we used to, we used to define an observable, which then we could associate with, I mean, we could take by probabilities that are associated with this observable. This is what led us to this whole formula. But those PB guys, PB, they as a solution to eigen problem of operator VB, formally they are just spectral decomposition of operator VB. So in other words, VB, you can write it as B over omega B, VB, B, PB, or even, you know what, can even be more fancy with that. If you take HBT, so this guy would just be equal to PBT B if we just rearrange and change the name of variables, we could map it onto a new set of operators. Okay, so in an event that there is some degeneration here, we can just redefine the eigenvalues and eigenspaces. So collect some projection operators that correspond to the same eigenvalue, and we could just, create in this way a new set of operators that are directly connected to eigenspaces and eigenvalues of operator VB. Okay. Let me consult my notes. So we can. So those operators that allowed us to define our B subsystem by trajectory, right? They come from spectral decomposition of Hermitian operator, right? VB. So we can generalize this observation, right? That whenever you have any observable, any Hermitian operator F, Hermitian, okay. It's Hermitian, so it has some spectral decomposition. So it has eigenvalues F, and it has a projection operators on the eigenspaces. And now those operators, right? We can do the same trick as we did with B, right? They can be now seen as a projection operators associated with measurements of observable F. Okay. So we can have F devices that measure this observable, and we can have by probabilities, by measures associated with it. Okay. On the other hand, we can see that systems interact with each other by coupling through operators, Hermitian operators, that have spectral decompositions, and thus can be identified with some observables, okay, that in principle could be measured with some dedicated device, okay, that's device that looks for decomposition into those projectors, okay. So in other words, this whole story led us to the very familiar notion that observables that could be measured by a classical observer are connected to Hermitian operators, right, through this spectral decomposition stuff, Hermitian operators that could play the role of interactions between systems, okay? So we just established the link between Hermitian operators and observables, okay? And this also gives us some clues that, if systems see each other by essentially but looking at the projections and eigenvalues of their coupling operators, and measuring devices also look for those things, for projections. So this kind of gives us a clue that perhaps measuring devices we were using so far, right, they most likely will come out or could be modeled as, in this formalism, as a system, as a coupled systems, right? So measuring device would be probably some special kind of system that is coupled to a specific observable that has a spectral decomposition corresponding to the measuring device we want to model. All right. And with this happy conclusion, I think we can finish for today.